This is topic 3B in computational methods in electrical engineering. The name of this topic is numerical linear algebra. The purpose of this lecture is not to present a comprehensive treatise on numerical linear algebra, but instead just to give you a small taste of what is underneath the hood of all of these different algorithms that MATLAB is running or other types of numerical packages. Primarily, we'll be talking about solving matrix problems like AX equals B or calculating matrix inverses, because those tend to be the fundamental building blocks of more advanced algorithms. Roughly, we can divide these methods into two different parts, the direct solution methods and the iterative solution methods. In the direct solution methods, we set up a loop and we ramp through that loop, and in exactly, let's say, 100 steps, we have our answer. Whereas in an iterative algorithm, we probably make a guess at the answer, and then we have another loop, but we successively improve on that until the changes in that answer fall below a certain threshold, and then we say we've converged on the answer. And there's always the chance that the iterative methods do not converge. A lot of people tend to prefer those for very large matrices and say that they're more accurate and can get to the answer faster. However, if you have poorly conditioned matrices, the direct solution methods are much more robust, albeit they can be slower when you have very, very large matrices. And last, we'll generalize all these algorithms for calculating matrix inverses. Our first method is called naive Gauss elimination. And it is naive in the sense that we are about to implement the simplest and most brute force way of solving a matrix equation. And there are some problems that can arise. We won't worry about them. We'll just pretend like they're not even going to be problems. They're easily fixable, but when we don't fix them, we just call this naive Gauss elimination. Our goal with naive Gauss elimination is to solve the problem AX equals B. And as I mentioned, there are some problems that can arise. It's fixable with a technique called pivoting. I'll mention it later on when I can point out that that happens, but we won't worry about it in this algorithm. We're just implementing the naive version of Gauss elimination. So we have to start off with a matrix problem. Here I'm just showing three equations with three unknowns put into matrix form, but you can generalize what we're going to do to any matrix size. So for illustration purposes, we're starting here with an AX equals B problem, three unknowns. Our next step, what we would like to do is eliminate references to the unknown x1 from equations 2 and 3, which will be in rows 2 and 3. So we want to somehow eliminate this A21 and A31. We will do that by subtracting row 1 from rows 2 and 3. However, we have to scale it in a way that will give us a 0 in the positions for A21 and A31. So I have here for row 2, we'll calculate a new row 2, and that will be the old row 2 minus row 1 scaled by A21 divided by A11. When we do this scaling and then the subtraction, we're guaranteed to get a 0 in this A21 position. Then for row 3, we do a very similar thing. We take the old row 3 and subtract row 1, now, however, scaled by A31 over A11. And that's what guarantees that we get a 0 in the A31 position. So if we were to be very brief in our language, we would just say we eliminate x1 from rows 2 and 3. The next thing we would like to do is now eliminate any reference of x2 from row 3. In other words, we would like to get a 0 in the A32 position. And we'll do this using the same technique we did on the previous slide. We will take the old row 3 and now subtract row 2 scaled by A32 over A22, and the prime superscript on A is indicating that those are our new values of A32 and A22 that we arrived on the previous slide. At this point, we will have a 0 in the A32 position. Notice now our matrix, what was the A matrix, is now an upper triangular matrix. We've mentioned this before, that when we have a triangular matrix, we're looking at a matrix that is almost solved. And in fact, what you'll see when we calculate x3, x2, x1 from this point, it's very, very fast and simple. So on to the next step. With this upper triangular matrix, if you look at the equation on the very bottom row, that is easily solved for x3. x3 is now just b3 over a33. And the double prime superscript is to indicate those are our most recent values of those that were calculated on the previous slide. So that's trivial to do. Then once we have A3, now we can go to the second equation and easily calculate x2. After that, we now have values for x3 and x2. We can then go back to the first equation and calculate x1. This process is called back substitution, and it's very easy once you have an upper triangular matrix. In this slide, this is dedicated to our observation that triangular matrices are almost solved. The majority of the work in solving AXB is in the forward substitution process, and that what gives us this triangular matrix. But once we have that, it's very fast and almost trivial to solve. And this is why triangular matrices, upper and lower triangular matrices, find their way into so many linear algebra algorithms, because they're so rapid to solve. And you'll see that in this lecture. Also wanted to point out, while we were doing the forward substitution part, we had to scale the rows before we did subtractions. And if you notice, those scales were highlighted in blue or made a blue color, and they're repeated here. I just want to point these out so that you can remember where they came from, because they'll come up again when we talk about LU decomposition. Our next method is the Gauss-Jordan method. This is an excellent method for solving AX equals B by hand or calculating matrix inverses by hand. So those are really the two goals of this method, solving AX equals B and calculating matrix inverses. You'll find it very similar to Gauss elimination we just talked about, with one difference. In Gauss elimination, we were forming an upper triangular matrix. We'll do the same types of row manipulations and subtracting one row from the next, but our goal will be to construct an identity matrix instead of a triangular matrix. And you'll see that as we step through the algorithm. So step one, we start with our matrix equation. Again, I'll only be doing a 3x3 matrix here, but this can be generalized to matrices of any size. So this is our starting point. Once we enter the algorithm proper, we have our matrix equation AX equals B. What we want to do is form what is called an augmented matrix. And that's what's being shown at the bottom of this slide. And it is a combination of the A matrix on the left and the B column vector on the right. We can think of it as a block matrix. And our goal here now is to do row manipulations until where we see the A matrix presently, we do our row operations until we get an identity matrix on the left. And when that happens, this last column will actually contain our answer, the x1, x2, and x3. But for right now, we just have this augmented matrix, and we go on to the next step. This is a methodical approach, so we set up a loop that will go row 1, row 2, row 3, through all of the rows that you might have. And once we're inside this main loop, the first step we want to do, whichever row we're in, we want to normalize that row by dividing by the diagonal element. Since we're in the first row, that diagonal element is A11, which means we divide this entire row by A11, and that gives us a 1 in this position. And of course, everything else is just divided by A11, and it ends up being whatever numbers we end up with there. So rather than keep writing all of those parameters divided by A11, we're just going to calculate a new A12, a new A13, and a new B1, and put the prime superscript on those to remind us that those are not the original A12, A13, and B1s, but they have information absorbed into them. In this case, they've been divided by A1. This step mirrors very much what we did in Gauss elimination. Our goal here is to eliminate reference to x1 from all of the other rows. So we're going to set up a loop that iterates through all of the other rows. And in this case, it's rows 2s and 3s. And our goal is to subtract row 1 scaled by something such that we will get zeros in the A21 and A31 position. When we do that, we get a new augmented matrix. And you'll notice that I'm using prime superscripts to indicate that we now have new values there after doing this operation. And so what you'll see for the new row 2, we will take the old row 2 and subtract row 1 scaled by an A21. And that's what guarantees we have a 0 in the A2 position after that subtraction. Same thing for row 3. It's the old row 3 minus row 1. However, the row 1 is now scaled by an A31, such that after we subtract, we get a 0 in that A31 position. The next step, the main loop in our program that is going row 1, 2, and 3, now we're in the second row, and so we normalize that row by dividing by the diagonal element. In this case, our diagonal element is A22 prime. And the prime, again, indicates that that is not the original A22. There's been some numbers absorbed into that. So we divide the entire row by A22, and that gives us a 1 in the A22 position. Now we're ready to go on to the next step. Now we enter our second loop, which is inside the first loop, and the second loop iterates through all of the other rows. And in this case, that is rows 1 and 3. The goal is to eliminate reference to x2 from equations 1 and 3, which means we want to get a 0 in the A12 position and the A32 position. We will do that by subtracting row 2 from rows 1 and 3, but we have to scale it by the right constant to ensure that we get zeros in the A12 and A32 position. So row 1 is the old row 1 minus row 2 scaled by the A12 constant. That ensures we'll get a 0 in the A12 position. Row 3 is the old row 3, also minus row 2, now, however, scaled by A32, and that scaling is what guarantees we get a 0 in the A32 position. Now we have our new augmented matrix, and you can start to see that the left side of this is starting to look like the identity matrix. And we're always doing this in 2 steps. We normalize the row, we subtract that parameter from all the other rows, and we keep doing this. Now we're on to the third row, and so we normalize the third row by dividing by the diagonal element. In this case, it's A33 double prime. When we divide all terms by A33 double prime, we get a 1 in the diagonal position. Now our goal is to iterate through all of the other rows. In this case, that is rows 1 and 2, to eliminate reference to x3 from equations 1 and 2, which is in rows 1 and 2. So we do this for row 1. We will take the old row 1 and subtract row 3, however, scaled by this constant A13, and that's what guarantees we'll have a 0 in the A13 position. Our new row 2 will be the old row 2 minus row 3, scaled by the A23. That's what guarantees we'll have a 0 in the A23 position. Now you'll notice we have the identity matrix in the left part of the augmented matrix. So the last part in this algorithm is to extract that very last column of the augmented matrix, and this is our answer. It's very important to do this extraction. Don't do the Gauss-Jordan method with your augmented matrix and at the very end circle the augmented matrix, because that is not the answer. The answer is hiding in that augmented matrix, and in this case it's in that last column. So when you pull it out, now you have your answer. Let's look at an example with actual numbers. So we're trying to solve ax equals b. We want to find x, and so we start our algorithm with an a and a b. So remember, we have two nested loops. This first loop will go rows 1, 2, 3. The second loop inside of that iterates through all of the other rows. So here what we do, we form the augmented matrix. You'll notice A is at the left, B is on the right, and now we can start these loops. And it starts by normalizing row 1 by dividing by the diagonal element. In this case, by coincidence, the diagonal element was a 1, so in fact the first row doesn't change at all. We then iterate through rows 2 and 3 and subtract row 1 from them. However, we're doing the scaling in a way that gives us the zeros in these two positions. And that's where x1 would be referenced by rows 2 and 3 that we wanted to get rid of. Now we move on to the next row. We normalize row 2 by dividing by the diagonal element. That gives us a 1 in the diagonal position. Then we start our next loop that goes through the other rows. And we subtract row 2 from rows 1 and 3 in a way that gives us zeros in these two positions. Now we move on to row 3, again dividing by the diagonal element. Then we enter our other loop, which removes reference to x3 from rows 1 and 2. And now we see that we have the identity matrix on the left, so that must be our answer hiding on the right of the augmented matrix. And remember, we're not done here. We can't circle the augmented matrix as our answer. We must extract the answer out. And then we have our answer. 024 in this case is the answer. So x1 would be 0, x2 would be 2, and x3 would be 4. Here's a written version of the algorithm. So step 1, we defined A and B. Step 2, we constructed the augmented matrix. At this point, we entered into our two nested loops. The very first one will iterate through the rows. And in our matrix only had 3 rows, so step 3 would be a 4m equals 1 to 3. The first step in that was normalizing the row by dividing by the diagonal element. Then our next loop started, which iterated through all of the other rows. And this is where we subtracted to put zeros above and below where we had a 1 in the diagonal position. And we iterate through all the rows. When that is done, the last column in our augmented matrix contains our answer. We have to subtract that out. And that's the Gauss-Jordan method. We can generalize this method. Instead of solving ax equals b, let's use it to find the inverse of a matrix. And we'll talk a little bit more about this at the end of this lecture. But now we only have to define matrix A. We don't need B anymore because we're not finding an answer X. We just want to invert A. So we form an augmented matrix, and on the left is A, just like it always was. But on the right, we're going to insert an identity matrix that is the same size as A. Then we do our Gauss-Jordan stuff. We iterate through all the rows. We have our nested loops. Everything looks the same. And we do that until where the A matrix was originally inserted will look like the identity matrix. And now what's on the right-hand side of the matrix is the inverse of A. And we're not done. We have to extract that out of the augmented matrix, and then we'll have our matrix inverse. So it's probably the best method I know of for calculating matrix inverses by hand. Our next method is called LU Decomposition. And recognizing that triangular matrices are very rapid to solve, the ability to decompose a matrix into lower and upper triangular matrix is a fundamental building block of many, many numerical algorithms. The first step in LU decomposition is calculating the upper triangular matrix. So we're going to start with our standard 3x3 matrix that we've been working with. And if you remember back to when we were doing Gauss elimination, we started with this. We did a forward substitution procedure, and we ended up with a matrix on the left that was upper triangular. That is what we do to come up with this upper triangular matrix. So our A matrix has changed. It's now our U matrix, our upper triangular matrix. And what was our B column vector, there's also new numbers there that we will call D. Our next step is to determine the lower triangular matrix L, and I think this is a pretty interesting thing. It turns out there is a lower triangular matrix. We can pre-multiply this upper triangular matrix and get our A matrix back. And even more interesting is what's inside this L matrix. It has zeros in the entire upper triangular part. It has ones going down the diagonal. And this lower triangular part are those L terms that I highlighted when we were talking about Gauss elimination. So in fact, there really isn't even any extra work we have to do to construct our L matrix. Those L terms fall out of the process when we're constructing the upper triangular matrix. So in a sense, it comes out of the process for free. At this point, we want to start with our original AX equals B equation. I'm then going to take the B column vector and move it over to the left side of the equal sign. So we end up here. At this point, I'm replacing A with L times U. The next step is to factor this L term out from both terms in this equation. So I factor out an L, and what that means is I need an L inverse pre-multiplying B. At this point, I can recognize that this L inverse B is actually our D column vector from the previous slide. So we put our D column vector here. So here is the LU decomposition algorithm. The first thing we do in step one is decompose A into L and U. And we use Gauss elimination to construct that upper triangular matrix. During those calculations, we're storing these L terms. And in fact, from there, we can build directly the lower triangular matrix just from those L terms. Now, a neat thing is done to make this a little bit more efficient. Remember in the L matrix, it had ones going down the diagonal and zeros in the upper triangular part of that. So in a sense, we already know those numbers. We don't have to store them. So instead, we can just put in the numbers for the upper triangular matrix. And the upper triangular matrix had all zeros in the lower triangular, so we might as well just store the L terms there. So in fact, it's a very efficient thing to do is just store L and U all in the same matrix, but recognize that they are actually separate entities. Now, if we want to solve AX equals B given L and U, it's a two-step process that are very, very fast and efficient. The first is we're solving the LD equals B, and since we have a triangular matrix, that's very, very fast. Once we have D, we can then use it to solve UX equals D for X, which was our original unknown. And that is also very, very fast. That completes our discussion of direct solvers. I now want to talk about iterative solvers, and the first one we'll talk about is called the Jacobi method. So, as I mentioned before, we tend to be interested in iterative solvers when the matrix size is very, very large, or perhaps when we have a pretty good idea of what the answer is and we can make a very good guess. In which case, if we have a good guess, it will take very few iterations to refine that answer and get it down to whatever accuracy that we want. But this is an iterative algorithm. And in general, in all iterative algorithms for solving ax equals b, we'll start off somehow with an initial guess. We'll calculate some sort of adjustment that we have to make to x. Then, of course, we make the adjustment to x, and we check if that adjustment is sufficiently small. If it's 10 to the minus 10 or something like that, we can say, you know what, we're finished. The details on that certainly changes from algorithm to algorithm, but all iterative algorithms have this basic flow to them. One thing we need to be careful of with the Jacobi method is that the matrix we're solving, the A matrix, needs to be what is called diagonally dominant. And the algorithm is very, very picky about this. So when you write the Jacobi method, I highly recommend in the start of your code, write in a little script to check and make sure it's diagonally dominant. And if not, return an error message. That will be much more meaningful than when your code errors out because it was not diagonally dominant, and then it's harder to find. So what do we mean by diagonally dominant? We need to make sure that each row is diagonally dominant. And the way we do that, we ignore signs. We just take the absolute value of all the numbers, and we look at the diagonal element, and then we look at the sum of all the other numbers in that row except the diagonal element. We need to make sure the diagonal is greater than the sum of all the other numbers in the row, and we have to make sure that's satisfied for all rows in the matrix. When that's the case, we call it diagonally dominant. So let's go through a bunch of examples. We have a little 2 by 2 matrix. Is this diagonally dominant? It turns out this is not diagonally dominant. If we look in that first row, the diagonal element is a 1. If we sum all of the other elements in that row, in this case there's only one other 1, it's a 2, well, that 2 happens to be greater than 1, so the diagonal here is not dominant. The second row, that satisfies being diagonally dominant, but all rows have to satisfy this. So that matrix is not diagonally dominant. Here's another matrix. And the question is this matrix diagonally dominant? This is also not diagonally dominant. The first row and the third rows are diagonally dominant. However, look at the second row. The diagonal element is a 1. And if we sum all of the other elements in that row, we get a 1. In which case that sum is equal to the diagonal element, and that's not sufficient to call your matrix diagonally dominant. So this matrix is not diagonally dominant. Next example, is this matrix diagonally dominant? It turns out yes. We have some negative signs in here, but since we're taking the absolute value of all of the arguments or elements in the matrix, we ignore that. We can pretend that they're all just positive numbers. In the first row, we have a 4. The sum of the other elements is 3. 4 is greater than 3. In the second row, we have a 3 in the diagonal position. If we sum all the other elements, we get 2, and 3 is certainly greater than 2. And in the last row, we have an 8 in the diagonal position, and the sum of all the other numbers is 5. 8 is certainly bigger than 5. So we have another diagonally dominant matrix. Last example, is this matrix diagonally dominant? And the answer is no. And in this case, we have 2 rows that violate our rule for being diagonally dominant. But it only takes 1 row to not satisfy our rule, and the matrix is not diagonally dominant. So the Jacobi method absolutely must have a diagonally dominant matrix in order for it to be guaranteed to converge. So before we discuss how to implement the method, I want to derive the equations used in the method. So of course we're starting off with our typical matrix equation, AX equals B, just 3 by 3 in this case. And again, the algorithm is extendable or generalizable to any size matrix. The first thing we'll do here is take that 3 by 3 matrix and expand it into the 3 component equations that the matrix equation represents. The next thing we'll do, we'll take the first equation and we'll solve it for x1. We get this answer. Then we take our second equation, solve it for x2. We'll take our third equation and solve it for x3. It turns out these are the equations that we will iterate. We'll have some initial guess for x1, x2, x3, and then we'll use these 3 equations to calculate our next version, or hopefully improved version of x1, x2, x3. And we keep doing this over and over and over. And what we'll see is that the changes from iteration to iteration will get smaller and smaller, and we iterate until that is sufficiently small. Now let's talk about the implementation. So at the start of this, we have to feed into our algorithm A and B, because that defines the matrix equation we want to solve. Next, we have to come up with an initial guess for x. Ideally, you know something about the physics or the science or whatever it was that created A and B to begin with that lets you come up with a good guess. If not, you're forced to just try different things. Maybe you set x to all zeros. Maybe you define random numbers in x. Maybe you can make good guesses as to just some of the elements in x and not others, and you use random numbers. You may have to try different things if you don't have a good initial guess otherwise. So we now have our initial guess, and we have our main loop. That's just going to iterate until every time we calculate new values of x, they're not changing very much. So we simply just iterate through our 3 equations for calculating our new values of x. Now there is a trick here. The first equation would work just fine. We're calculating a new value of x1 from old values of x2 and x3. So that would work just fine. Now, if we just type this into MATLAB blindly, we could accidentally be using the new value of x1 instead of the old value. This should be the old value here, not the new value. So in fact, when you're calculating these, normally in MATLAB, you would calculate an x1 new, an x2 new, an x3 new, and that way you can still use the old values, and then just copy it over when you're done. So once you have the new values of x, you move on to step B here, and you calculate how much they've changed. And we look at the difference between the new and the old values, and maybe we add up all those differences, and we're constantly monitoring that. And we wait until that difference between the old and the new values is sufficiently small. And we'll probably pick a number like 10 to the minus 10. And then we're guaranteed to have 4 or 5 digits of accuracy in our final answer. So it really is that simple. Now, we really would much prefer to implement this using matrices instead of algebra because it's more easily extendable to large matrix sizes. So let's think about this. We started off with our 3 equations that we use to iterate. What I can do now is just write these in a slightly different form. Now, you may have to think about this for a bit and stare at it for quite a while, but it turns out by observation, we can take this and write it directly in matrix form. So what I like to do is first, look at these terms in parentheses. Those really are our original equations, just without the diagonal terms. This first equation, which used to have an a11 times x1 over here on the left, is no longer there. x2 is no longer in the second equation, x3 is no longer in the third equations. So it's our original equations minus the diagonal terms. So we can write this in matrix form as our original matrix A minus the diagonals in A. So now we'll have A again, but just zeros running down the diagonal, and that multiplying our x column vector. So this product of terms here will give us these three equations and minus those diagonal terms. Then we're subtracting that from our B values. So we need to subtract that from our B column vector. And then notice on the outside, we're dividing by the elements of A which are along its diagonal. So we pre-divide by the diagonal of A. So this is the matrix equivalent of these three equations. And here's just to remind us what the diagonal of A is. So it's all zeros except just the diagonal elements of A running down its diagonal. So for simplicity, let's let D equal the diagonal of A. So D for diagonal. That lets us write our previous equation from the previous slide this way. We had an A minus diag A here, and we had a diag A over here. So now we just write that as a D and an A minus D. We then do a bunch of matrix algebra, and we end up in a form that gives this some pretty good physical meaning. And we have the new value of x equals the old value of x, or the previous value of x, plus some kind of improvement to x. And I like formulating my equations this way because it lets me calculate the improvement on x, which I can then do two things with. The first thing I'll do is use that to improve our value of x, but the other thing is I can use that improvement to see how big it is to see if we're finished. So here's the entire algorithm written out. Step one, we're going to define our matrices A and B, although maybe you could say that's not even part of the algorithm. Those are inputs to the algorithm. And maybe even step two is outside of the algorithm. Somehow we have to make an intelligent guess. And maybe we're just all random numbers. Maybe we know something about the physics of our problem that makes us or lets us make a good guess. Really, step three is where we enter the algorithm proper. And the first thing we'll do is we'll extract the diagonal of the A matrix. And in MATLAB, it's just simply D equals diag of A. And it knows to pull the diagonal out of A. Then we enter our main loop. And the first step inside the main loop is to calculate this adjustment of x. This will tell us how much we need to change our x column vector to get to our next better solution. And so in MATLAB, that's just dx equals d backward divide b minus a times x. So we're pretty much just typing in what we see here. And remember, once we have that delta x, this is the thing that we'll do two things with. We'll use it to improve x. We'll also use it to calculate our error. So that's the next step. We update our values of x based on this adjustment, and then we calculate the error. And we iterate until that error is sufficiently small. And that's it. That is Jacobi iteration. I have a block diagram of this method, which may let us visualize a little bit better. So here I'm showing the input arguments as a, b, and x. X may not be an input argument. It might be in the algorithm where we just fill it with random numbers. So step one, we extract the diagonal of A, and we call that D. Then we enter our main loop. And are we done? Well, we just started, so we're not done yet. We calculate the adjustment, we adjust, and we use the adjustment to figure out how much we've adjusted. And we keep doing this until that adjustment is sufficiently small, and then we're done our algorithm. The last topic in this lecture is calculating matrix inverses, and we only have two things to discuss here. One is using the Gauss-Jordan method. As I mentioned before, What we want to do now is construct an augmented matrix with A on the left and I, the identity matrix, on the right. A is the matrix that we want to invert. So our augmented matrix will have A on the left and an identity matrix on the right. Now we do the Gauss-Jordan method. We do our row operations, subtracting rows from other rows, scaling, and we do that in a way that gives us the identity matrix on the left, and what we end up with on the right is the inverse of A. So we implement it exactly like the Gauss-Jordan method for solving AX equals B. We just have a few more columns on the right, and when we're done, we extract that out, and that is the inverse of A. This is my favorite method of calculating matrix inverses by hand. Of course, I don't like calculating matrix inverses by hand, especially when they're large. I much prefer doing that on a computer. We can also calculate matrix inverses with LU decomposition, although what I'm showing here really can be generalized to any technique you have for solving AX equals B. We can use that to solve for matrix inverses. So what we'll do is we'll solve for AX equals, and instead of an arbitrary B vector here, we're going to put a 1 in the first row and a zeros in the rest of the positions. Put a 1 in the first row, zeros in the other. When we solve this, what we actually get is the first column in our A inverse matrix. To get the second column in our inverse matrix, we now put a 1 in the second row and a zeros in the first and third. When we solve this matrix equation, the answer is the second row in our matrix inverse. And you can probably guess what's going to happen now. To get the last row, we put a 1 in the last position, zeros in all of the other positions. When we solve this little AX equals B problem, we get the third column in the matrix inverse. So really, any method we come up with for solving AX equals B, we can generalize it using this method to calculate matrix inverses. And that is it for this lecture. Thank you very much.